Okay, how many of you started MP2? How many of you have started MP2? Okay, get started today, okay? We extended deadline for MP1 until noon Friday, mostly because a few of you had trouble logging in, okay? But you should have been done by now, yes? It's not posted yet? Okay. That's... Well, okay, thanks. It will be, it will be posted, okay? Okay, so last time we ended right around here, and we said that every thread block is going to be assigned to one of the streaming multiprocessors, and the thread blocks are going to be divided into these 32 thread warps, okay? And you can have any number in your thread block from 1 to 1,024. And if you have 3 threads in a block, it will work. It's just that you're going to have a first warp with only 3 threads, right? And then the warps are 32, so you're going to have 3 threads that are active, and then 29 threads that are inactive. So you're guaranteed to have what we call the divergence in that thread execution, but it will work correctly, okay? And you should try these things. So now, when we assign blocks into streaming multiprocessors, we have this concept of occupancy. You can actually assign anywhere between 1 and some number. And in Maxwell, it's 32 thread blocks, okay, up to 32 thread blocks. Into a streaming multiprocessor. So let's say if we ended up assigning 3 thread blocks into the streaming multiprocessor, and each thread block has 256 threads in our example that we showed, then how many warps are there in the streaming multiprocessor? It's very simple. There's not a trick question. 3 thread blocks, and each thread block is divided into 8 warps, 256 divided by 32. So the answer is 24. Okay, so it's fairly easy. So what that means is that when we assign these 3 blocks into a streaming multiprocessor, these 24 warps are going to be in a pool for execution. Okay, so they're going to be coming in and out of the real execution units in that streaming multiprocessor. So this brings us to the concept of scheduling. Okay, this is the biggest difference between GPU architecture and CPU architecture. The CPU architectures also have the concept of threads. But in CPUs, when you switch from one thread to another thread, there is a fairly high overhead for context switching. You need to save the registers. You need to change a lot of the mapping processor control registers and mapping registers protection and all that stuff. It takes probably a couple thousand instructions for most of the CPUs to switch from one thread to another thread. In GPUs, the thread scheduling is what we call the zero cost. There are enough registers for all the threads. So you're not going to be saving your registers in order to run another thread. You're just switching from one part of the register file to another part of the register file when you switch execution from one thread to another thread. And in reality, we're not just switching from one thread to another thread. We're switching from the execution of warp to other warps. Okay? And whenever a thread in a warp goes into execution, the rest of the other threads in the same warp will also go into execution at the same time. You can think about these warps as essentially, sort of the platoons in the military. When you send a platoon in, everyone will go in. Okay, so that's essentially what it is. And so we have this what we call the zero overhead scheduling. And so we can switch the execution of from one warp to another warp without any cycle in between. Okay, so you can just essentially, switch around with no gap cycles. So these warps whose next instructions has its operands ready for consumption are eligible for execution. So basically what we're saying here is all those warps in the streaming multiprocessor are going to be tracked. They're going to all have a program counter. Every one of these warps will have a program counter. And the program counter will tell you which instruction will be executing in that thread, in the threads of the warp. Remember, these are single instruction multiple data. So all the threads in a warp will be executing exactly the same instruction. And you're also going to look at the operands for those instructions. And the hardware will tell you whether those operands are ready for access. Because some of the threads may be consuming a memory access data, a load instructions data. And that may take hundreds of cycles. So some of these warps may be waiting for data that are not there yet. So they're going to be put to rest. Okay, they're not going to go into execution. They're going to be sit on the bench. Okay, and as soon as their operands come back from memory and so on, they will become eligible for execution. So the hardware will have a priority mechanism, which they don't tell us how they do it, to select from the warps whose operands are ready, and they will select the next warp for execution. Okay, so this is scheduling. And all these threads in a warp will execute exactly the same instruction as when selected. So here we show it a little conceptual example. This picture is far from far from, I would say accurate, but it's sort of a higher level concept that you should keep in mind in your mental picture. So what we're showing here is we're going to have 3 thread blocks, TB1, TB2, and TB3. So those three thread blocks will have their warps in the mix. And so every warp is identified as thread block with a thread block number and a warp number within that thread block. So we'll have thread block 1, warp 1. It will execute for a little while until it hits an instruction that requires an operand that is not ready yet. So that may be a add instruction that will be using a load instruction result. But that load instruction is still executing in the memory. Okay. So at that point, it will switch. It will switch to the next thread warp, which is, in this case, thread block 2, warp 1. And that warp will execute for a little while until it hits an instruction that uses an operand that is not ready yet. So now you see the trend, the pattern, right? You execute whatever is ready to execute for as long as you can, and then suddenly you hit an instruction whose operand is still being produced by someone, taking a long latency. You switch to another warp for execution. So this is really, really, an interesting contrast to out-of-order execution that you will be learning or you have learned in 4.11. In 4.11, the processor has very similar goals. Okay, so whenever you have an instruction that is waiting for a operand that will take a while to produce, the out-of-order execution will try to pick an instruction within the same thread, and reorder the execution so that some of these other instructions in the same thread will go execute. And GPUs don't do that. What GPUs do is they pick an instruction from other warps and execute another warp while putting all the threads in this current warp to rest. Okay, so that's really the fundamental difference between most of the GPU hardware and the CPU hardware today. I see a question.
Yeah. So I'm concerned about they will consume the same register format. What if there's conflict? So when will they kind of clean up the thing? It's not.
Yeah. Yeah. So so they will be executing accessing registers. That's a very good question. So whenever you say access register R1 in your kernel code, okay, so ultimately your CUDA code is going to be compiled into assembly code. Okay, there's no escape about that. So in your assembly code, in fact, in the next few slides, I'm going to show you quite a few of those today. And so when you say register 1, it actually means 32 registers register once. Okay, there are actually 32 registers, all being accessed, each one being accessed by one of the threads of the warp. They're all different registers. So that's why there's no real conflict in that sense. They're still accessing their own registers and so on. Okay, but there will be more details later on today. Yes?
So after they execute the next warp, can they come back to the previous warp?
Okay, so after you execute the next warp, do you come back to the previous warp? One of the previous warps. So the warps are going to be in 3 different states. Okay, executing state, or eligible for executing stage, or just waiting. Okay, so when the executing warps hit a instruction that forces it to wait, you will pick from a pool of eligible warps. It will be one of the previous ones, but may not be exactly what you think it is.
And does it come back to the one that's in the waiting state?
It would, no, it does, these are the policies that they don't tell us, and they don't want you to know. Okay, yes?
Is the policy, or I guess the hardware described for how they do this no-cost context switching? Like, is that something that NVIDIA publishes, or is that internal?
In general, we know the kind of okay, the question is, do people publish these kind of scheduling mechanisms? The answer is yes. There are many, many papers about this. Whether or not those papers correspond to reality, who knows? Okay, yes.
So when you say all threads in a warp execute the same instruction, does that mean like when we're executing on a warp, all the threads are executing in like true parallel?
Yes. So the question is, when you execute an instruction in a warp, are all the threads in that warp truly executing in parallel? The answer is, in the early GPUs, the very, very early GPU G80, there are only 16 execution units in a streaming multiprocessor. So what happened is that when you execute a warp, you'll have essentially take 2 cycles. The first cycle you send 16 down the pipeline. The second cycle you send another 16 down the pipeline. Ever since then, all the streaming multiprocessors are pretty much big enough to have a minimum of 32 execution units. So you can think about all the warps are now truly executing in parallel. However, hopefully by now you should know, it should be clear to you, that even though you have 24 warps, right, in our example, all active in some way in the streaming multiprocessor, they may or may not be all really executing in parallel at any moment in time. Some of them will be resting, some of them will be eligible waiting, and some of them will be executing. Okay? In the most recent streaming multiprocessors, there are enough hardware units to have multiple warps all really executing at the same time. Okay? Yes?
There's divergence among the within side of warp.
Coming up. So what about divergence? So I'm going to call you Mr. Divergence. But this actually go away. So you know what? Have you seen the movie Divergence? Okay. Good. So at least we have a little bit of generation gap, but at least you're aware of some of the more recent ones. The divergence here is actually not that different from the divergence concept in the movie. Okay. So we'll definitely come back to that point. Yes.
So are interrupts handled any differently here than they are like on CPU?
Okay, so is interrupt handler here the same as the CPU? The real answer is GPUs don't really handle interrupts.
So they're just all masked?
So they actually don't do much about it because, remember, this is a heterogeneous computing environment. So these GPUs don't really serve external interrupts. The CPU tend to take that work. Okay. There's a little bit of subtlety in that because we have some more recent architectures that will do what we call the RDMA kind of things. So there's some subtleties involved, but let's stay away from that until you take 508. Okay. Any other questions? Okay. So, Mr. Divergence, where are you? Pay attention now. Okay. So here is the concept of control divergence, okay? And so this is actually one of the main performance concerns with, in the GPU. So the concept is that threads within a single warp would, can potentially take different paths. Remember in the kernel code, in the vector addition, we had that test whether the index I for a thread is within the length of the vector. So if it's outside the length, then you know what, you should not do anything. So we have that if then else. And if you look at the example of 1,000 elements, the last warp, the last block is going to have some of the threads within the range and some of the threads that would not be within the range. So if you look at the very last warp in the in that example, the last 32 threads in the last thread block is going to have 8 threads. Okay, it's 1,000, so it's going to be 8 threads inside the range and 24 threads outside the range. Okay, 1,024, 1,000 elements, so 24 of the threads will be outside and 8 of the threads will be processing, right? So that warp is going to have a situation where some of the threads will go in one direction and some of the threads will go in the other direction in that control, in that if then else statement. So this is called control divergence. And the different execution paths in this case, in the GPUs, will be serialized. So instead of having some of the threads executing on one path and some of the threads executing on the other path in parallel, the way that GPUs handle this is by having everyone to go down the true path, but not allowing the path, the threads that failed that test to actually commit their execution result. So they will still do the work, but then their outcome will be thrown away. They will not be allowed to change the processor state. And for those of you who learned 411, you also have a situation of branch prediction, and some of the results will not be allowed to take effect in the pipeline. These are not that different. Okay. Now, then the execution will go back and have every thread in the warp to also execute the else path. And in this case, it's the opposite. The threads that fail the test will now be allowed to change the execution state, and the threads that succeed in the test will not be allowed to change the processor state. So when you have a control divergence, you will begin to see a situation where the execution actually got longer, because you actually take one pass for all the threads to give the chance to the succeeding threads in the if condition to take effect, and then you take some more time for all the threads to go down the else path, but only allowing the failing threads in the if test to take effect. I saw a question.
So this is just predication, right?
This is not predication at all. Predication, I was Mr. Predication 20 years ago, and I told people that you should use predication. It turned out that in order to reduce the overhead of this control divergence, NVIDIA eventually adopted our predication scheme. So in some cases, what they will do is they will use a predication mask and then allow all the instructions to be able to go down together, but using the predication path scheme to enable, disable the instructions so that they don't need to go these multiple passes. The predication is, has a little bit of limitations, so it does not apply to all of them, especially when the paths are, very uneven. Okay, so it does help, and it does help to a quite large degree. In fact, most of the code that the compiler generates today use predication for exactly that reason. So it's used to mitigate this negative effect. But fundamental problem is that, in general, if you use control branches, you branch around in your code, then you will see this divergence. And if you use predication, you can eliminate some of these branches, but essentially, qualify your execution result with the predicating mask, and then you don't need to do this multi-pass thing. Okay, very good. So a common case for this, so this is the beginning of, making these kind of, you should be able to know exactly when the control divergence happened in your code. So let's begin to do some mental exercise. The reason why you will have control divergence is because your if condition, if statement involves in some way the thread index. If your if your if condition or loop, let's say loop iteration condition does not involve in any way thread indices, then all the threads will be going in one direction or the other direction together. The only reason why you will have a different decision outcome for these if statements or loop statements across threads in a warp is because the if condition or loop condition depends on thread index, right? So that's the first test. If if your condition does not involve threads, thread indices, then there should be no control divergence. So if the condition involves thread index, then you can see, for example, here, if we have a test of thread index is greater than 2, then we have a control divergence problem. And the control divergence only happens in warp 0 in the thread block, because the only warp where the threads can potentially make different decisions is when there are thread indices 0, 1, 0 and 1 and 2, right? They will make a different decision than the thread with thread indices greater than 2. In warp 1, warp 2, warp 3, all the thread indices will be greater than 2. So they will still be making exactly the same decision within that warp. So even when you have a thread index involved, it doesn't mean that there will be control divergence within all the warps. Okay. Most of these boundary checking kind of conditions will usually involve only the control divergence only in one of the warps. That's the warps that contain the threads that have on both sides of that boundary. Okay, so that's the most important concept. And you're going to see most of the control divergence that you're going to use in this class belong in that category. It's the most important category of control divergence because we need to use boundary checks to make sure that our code is correct. But the use of control divergence in these kind of codes actually have very, very minimal effect, because only one warp out of many, many warps in your data structure. If data structure is big, you're going to have many, many warps that are operating entirely in the valid range, or many, many warps that are operating entirely outside the range, and only a small number of warps that are operating right on the edge will have this divergence. It's going to be minimal performance effect, and it gives you the correct functionality. Okay, so but in some other cases, things may be a little bit more subtle. So, for example, if you have a thread index.x divided by warp is greater than 2, then this thing will not cause any control divergence in the code, because all the thread indices divided by warp size will be either entirely, all the threads in the warp will end up with exactly the same number, right? So, that's why all the threads, all the warps will either make the if path, or all the threads will go down the else path. So these are the kind of decisions that you should be able to make about control divergence by just looking at the code and the nature of your data. Now, so let's take a quick look at some of the interesting granularity considerations. Whenever you have flexibility for the programmers, you also give responsibility to the programmers. So this is the reason why whenever we begin to expose more and more of these design choices for the software developers also need to know more about the architecture and the sort of the real implications of these things. So here, what we have taught so far is that you can assign certain number of thread blocks, up to certain number of thread blocks, into a streaming multiprocessor. We also told you that you can assign up to so many threads into a thread block. We also told you you can assign up to so many threads into a streaming multiprocessor. Those two numbers are not the same. Okay? The streaming multiprocessor can take up to a certain number of threads. For example, in Maxwell, you can take up to 2048 threads in the streaming multiprocessor. And it depends on the number of threads in a thread block. You'll have more or fewer blocks that account for up to 2048. So here, let me use a very small example to illustrate some of these potential constraints. So for this color to grayscale conversion, should we use 8 by 8 thread blocks, 16 by 16 thread blocks, or 32 by 32 thread blocks if the GPU use can only take 1,536 threads and up to 8 blocks? This is the Fermi generation. So you know what, in the Fermi generation, each SM can take up to 8 blocks and 15,036 threads. So let's go through the exercises. 8 by 8, 8 by 8 thread blocks, that gives us 64 threads. 2 warps. There will be 2 warps in the thread block. Fine. Okay. From the warp point of view, it's not bad. But since each SM can take up to 1,536 threads, that means that for the 8 by 8, we can accommodate up to 24 blocks, right? From the thread point of view, right? The streaming multiprocessor can take up to 1,536 threads. So because every thread block has only 64 threads, theoretically we should be able to accommodate 24 thread blocks just given that thread capacity. Okay? However, each SM can only take up to 8 blocks. So that other constraint will kick in at 8. So it will say, I can only take 8 blocks, and so every block will bring in 64 threads. So in reality, this streaming multiprocessor will only take 8 thread blocks times 64 threads, and that gives you 512 threads. So essentially what this means is that every streaming multiprocessor has these limitations. It has a limitation on the thread blocks, number of thread blocks. It has limitation on the number of threads. So if these things are not balanced, you can have a situation where you ended up taking only up to the 8 blocks because that's the first constraint that will hit you. And that means that you can only bring in 512 threads. You are not fully utilizing all the thread capacity. Why is this the situation? This is because every thread block requires some sure resources for all the threads. So you need to build hardware to be able to support all the thread blocks, keep track of the progress of the thread blocks, support the barrier synchronization of these thread blocks. So every generation of streaming multiprocessor has some number of thread blocks that it can support. Every thread also has some resources. Every thread requires, some kind of resource to keep track of the operand availability. It needs to keep track of, some of the control registers and so on. These things still exist in the GPUs. It's just that they provide you so many that a lot of the threads can be simultaneously active. So, in this processor, it provides 1,536 threads worth of resources that it can track. So whichever limit is hit first, it will become the limiting factor. Right? So in this case, we will only use 512 thread out of the 1,536 number of thread capacity. So we're not fully utilizing the thread capacity of this streaming multiprocessor. We only have 512 threads or 16 warps in that matter. Divide by 32, you have 16 warps that you can schedule. Okay? Now, 8 by 8. So if we go to 16 by 16, we'll have 256 threads in each thread block. So that means that from the thread capacity point of view, we can we would end up with 6 thread blocks, 1,536 divided by 256. So we only need to take in 6 thread blocks to fully utilize all the thread capacity. 6 and 1536 is exactly the capacity. It still fits into the capacity of 1536 and 8. So in this case, the block capacity does not kick in, right? The block capacity has 8, and you only need 6 to be able to bring in everything. So this is the incentive for this particular hardware for you to use a bigger block size, 16 by 16, not 8 by 8. Okay? And when you use it this way, you will end up with 48 warps that you can schedule. Okay? And this will allow you to better utilize the tolerated memory latency and make better use of the hardware resources. You will have faster execution on this processor. How about 32 by 32? If we keep increasing the block size, 32 by 32 means that you have 1,024 threads in the block now, right? 1,024 threads in the block means that you're going to have a little bit of a problem because one thread block is within the thread capacity, but when you try to use 2, you're going to be going beyond the capacity. So you end up hitting the thread capacity when you try to bring in more thread blocks. So you're only going to be allowed 1 thread block because of the thread capacity. So you are using only 2/3 of the thread capacity simply because you have a quantization problem. Bringing in 1 more thread block will bring you over, but you still have half. So this is the reason why you cannot use very big thread blocks for this architecture. So these are the kind of things that for a GPU programmer, it's actually quite complicated to calculate. That's why NVIDIA, right from day one, we told NVIDIA, you need to have a calculator for people to be able to figure this out. So NVIDIA provides this occupancy calculator, and it will tell you tell NVIDIA which generation of GPU you need to use, and then it will tell you the kind of for any kind of blocks size design what kind of occupancy you're going to get. And in 2010, we published a paper, search space pruning for the GPU programming, and it just won the Test of Time paper award this year. And because it's such a big problem that a lot of people actually refer to this paper and use the solution that we have in that paper. Okay, so we are done with lecture 3. So now you understand a lot more about thread blocks. You understand a lot more about warps. You understand the streaming multiprocessor to the kind of the beginning level, and you begin to get to know Mr. Divergence. Okay, so let's begin to to look into the data side of the architecture. So we're going to talk about memory model, and in parallel computing. Ultimately, a lot of these things, that we talk about have thread management and so on. These are absolutely, necessary. But in the end, when you start to really work on these, real applications, you will realize that the data tend to be the real limiting factors. A lot of these control things, the limitations are easy to figure out. Okay, they're quite easy to figure out. But for memory, you will need to oftentimes reorganize your data structure. There are certain techniques that you need to use in order to reshape your data accesses. And those are the kind of things that we're going to be spending a lot of time in this class to teach you the knowledge that people accumulated over decades for these kind of things. So we're going to learn the basic features of the memory accesses by the CUDA threads. Okay. And we're going to prepare for MP2, which is the basic matrix multiplication, and which is going to be due next Wednesday. Okay? And then you're going to learn to evaluate the performance implications of global memory accesses. My friend, David Padua in computer science, once said something famously. He said that any graduate student who wants to study computer architecture if the student cannot write a matrix multiplication code on the blackboard on demand, the student does not deserve to pass the qualifying exam. And I totally agree with that. Matrix multiplication is one of the most studied, computation in the world. And, matrix multiplication has produced thousands and thousands of PhD theses. Just the optimization of matrix multiplication has produced, I would say, thousands of PhD theses. And for any PhD student who want to study computer architecture, compilers, and so on, this is the first thing you need to understand. Okay, so this is not your hello world, but this is, the entry-level computation for real, for real parallel computing. And sure enough, if you look at all the machine learning, the neural net implementations, the best neural net implementations typically involve formulating the convolution layer and all connected layers into what? Matrix multiplication. Okay, so we're going, there'll be some, several series of lectures leading to that. But by the middle of this course, you will get to know matrix multiplication extremely well. Okay, even better than Mr. Divergence. So what is the, let's start with the CUDA memory model. And, this is going to be the kind of the mental picture that you should be keeping for the rest of the semester. As a CUDA programmer, you're going to, you're going to be writing kernel code. And remember, the kernel code is going to be executed by all the threads in your grid, right? And so every thread in this architecture can read and write per thread registers. Okay, so if you generated thousands of threads, okay, and every thread will have its own stash of registers. And the thread can read and write its own registers. The threads cannot read each other's registers. So that's why it's called per thread registers. How many registers are there? Tens of thousands in each SM. Tens of thousands of registers. How many registers do we have in the x86 architecture? 8 or 6, depending on your definition. Up to 8. Right? And then you have the 64-bit extension that brings you 32 registers and so on, right? So in each SM, in this architecture, there are tens of thousands of registers that will be allocated to the threads. But once you allocate these registers to a thread, it's only going to be read and written by that thread for the duration of executing this grid. Okay, so per thread registers, and these the data in the registers can be accessed in the order of 1 cycle, extremely fast. Okay, now the second type of memory is read. Every thread can read and write per block shared memory. Okay, the shared memory is a batch of special memory, what we call the scratch pad in general, and these memory locations are shared among all the threads in a block. So when you allocate shared memory, you're allocating shared memory for a particular thread block. Okay? And other thread blocks cannot see the contents of your shared memory. Okay? And these shared memory locations can be accessed reasonably fast, maybe about 5 clock cycles or so. Okay? In 5 clock cycles, you can read, write that location. The next level is you can read and write per grid, global memory. And per grid means that when you launch a kernel, you have all the threads in the grid, and all of them are going to be able to see the contents of that memory. So when you remember the CUDA malloc, when we allocate memory through CUDA malloc, that location is in the global memory. So all the threads will be able to read or write to the data. So these things are accessed in the order of about 500 clock cycles. Okay, every time you go and read something from the global memory, when you try to write to the global memory, it takes about 500 clock cycles. That's eternity, essentially. And then you can have something called constant memory, and you can read only per grid. Every thread can see exactly the same constant memory, and these are usually used for parameters and so on. So things like, weights, when you make inference and so on, those are read-only accesses unless you train, right? So when you do the inference, these weights can be put into constant memory. And these are, about 5 cycles with caching. They're, usually cached extremely successfully in these architectures. So we have not exhausted all the memory types in this architecture. There's texture memory, but we're largely not going to worry about that, in this course. So some people think that GPUs are magic, okay, and let's just throw that out of the door right away, okay. GPUs are not magic. GPUs are hardware that ordinary people design, and they're designed in somewhat different ways, so they may look a little bit different, but they're still following the fundamental von Neumann model that all of you learned in ECE 120 or the equivalent course. So John von Neumann, drew this picture. This is a picture that he drew in the 1940s, and he said, here, when we build a processor, we have 3 important things, and then one kind of peripheral. We have the processing unit that has the ALUs and the register file, and then the processing unit will be controlled by the control unit, where there's a program counter, and then you fetch instructions, and then you put that into the instruction register, and you use the instruction information to control your execution. And this was a radical concept in the days of John von Neumann, because before this day, most of the computers were fixed function computers. They were calculators. But here, with the concept that you can fetch something from your memory and place that into the instruction register, you look at the instruction and decide what the computer does for that instruction. It's called store program computer, and that changed the world, because now you can reprogram the same hardware to do very different things, right? So this was the reason why he's so famous. And but the concept has been kind of, I would say, created by a small number of people, including Maurice Wilkes and so on, in that period. Now, in order to process data or fetch instructions, you need to deal with that memory, right, up there. So that memory used to be built with cores. Okay, this is why we still call some of these things core dump, and the in-core algorithm. These things used to be designed with electromagnetic cores, and they look like this, and then you have a wire going through it, and then they will have a different magnetic orientation depending on the direction of the current in each of these cores, and then they will be the 0s and 1s. Obviously, you cannot build very big memory out of that. And then we went into the transistor memory, then we went into the integrated memory, and so on. So, now here we are in the order of, gigabytes of memory in that thing. But it's still fundamentally memory. And then you have the I/O, that you can access. So let's go back to the program. All these statements, okay, all these statements that you write in the kernel will be compiled into instructions. And so everything that you learned in ECE 120 and 220 are still true. Okay, we have not invalidated anything that you learned in those classes. So each instruction that you generate out of the kernel program needs to be fetched from memory, decoded, and executed. Okay, so what you learn in 411 and so on will be exactly, pretty much exactly applicable here. And so the decode stage typically accesses the register file. Okay, so when you decode the instruction, you find out, oh, so there are source registers, 2 source registers, 1 source register. You go and fetch the register file. So this is the 411, instruction decode stage pipeline, right? And those are exactly the same. So the decode stage will access register file. That's the reason why when you place a data in the register file, it's free for all the instructions to access because it's part of the decoding of a ALU instruction. It's part of the decoding of memory instruction. When they are decoded, the data gets fetched. And you don't need to have another instruction to get it out of the register file in order to use it. Okay, so this is why we call registers are essentially free. And these instructions come in three flavors. Operate means mostly arithmetic and logic, and then data transfer, which means loads and stores, and then control, which means branches. Okay, so those are the three big flavors. And so instruction cycle will be fetch cycle, decode cycle, execute cycle, and memory cycle. I'm not teaching 411 here, so you know what? Trust me, you're not going to see a whole lot more of these in this class. But there are a few things I have to make the connection, so that you're going to really understand some of the things that we're talking about, rather than memorizing everything. So when we execute an operate instruction, which means probably arithmetic instruction or logic instruction. So, for example, if we do an add instruction, and here we use the convention that the first register is the destination register, and the other two registers are source registers. So the instruction cycle for the operate instruction will be you fetch this add instruction, you decode the add instruction, and you get R2 and R3 out of the register file for you. And then you execute and generate the result, and at some point you write back into the register file. And for the memory access instruction, this is the notorious load instruction or store instruction. Remember, these instructions will access either the shared memory or the global memory. Okay, they will access either one. And it will become very clear in your kernel code. So the kernel code, you would place some of the variables and arrays into shared memory, or in the host code, you may allocate some of these data structures in the CUDA-malloc global memory. Anything you allocate through CUDA-malloc go into the global memory. Okay, so far you only have access global memory data. Okay, so when you have a load instruction, R1, R2, R1 is going to be the destination register, and R2 is going to be the source of your index or the offset register, and then you have offset number 2. So you will, in the decode stage, you're going to access R2, and then in the execute stage, you're going to add R2 with the offset number 2, and then in the memory access, you actually go out, do the virtual address translation, access data. GPUs also have virtual memory management, by the way. Okay, you don't escape any of that. So hopefully this is the lecture where I debunked the concept that GPUs are magic. Okay, GPUs are totally different alien animals than the CPUs. If you look at the construction, they're very much the same. It's just that the design philosophies are different, and then certain techniques are not used in one versus the other. And so that's the execution. So here is an important slide for you to remember: registers versus memory. Okay, registers are free. Instructions essentially grab the register value along the way when they are decoded. And so no additional memory access instructions. When we use shared memories are going to be fast, but shared memories still require additional load instruction or store instruction. Okay? So that's why I bothered to spend this time to make sure that you really understand. And they're very, very fast to use. However, there are very few of them. How few? Tens of thousands in each streaming multiprocessor. That's a small number, by the way. Okay, so memory is expensive, very slow, but very large. There are gigabytes of them in the storage. So think about registers, the number of registers as Professor Hu's bank account balance, and think about memory capacity as Bill Gates' account balance. Okay, that's about right. Okay. So now going back to the programmers. So when you write a kernel code or host code for the CUDA program, you can direct these variables into different storage hierarchy. So this is the beginning of the Mickey Mouse direction of the orchestra in Fantasia. Okay, so you should definitely watch that segment. I think YouTube has a little snippet of that. So if you intend to put a variable into registers, you almost need to do nothing. In your kernel, every time you declare a local variable, a C local variable in your kernel function, it will be placed into registers. If you don't say anything, remember the I that you produce, the I variable that you produce out of the thread index and block in, that I is in the register because it's a local variable in the kernel. Okay? So you took one register per thread and you generated 1,000 of those threads, right? So you are using 1,000 registers right there. Okay? You already used up 1,000 registers just by declaring the I. Yes?
There's still like a runtime stack too, right? It's not just like using all registers for everything.
So the question is there a runtime stack and then you're not using registers everything? The answer is actually close. The answer is you are using all the registers. So the hardware will not admit your program if it used too many registers. So there's something called register spilling, and it's actually terrible. So you don't want to get anywhere close to that. Okay. So the reality is the runtime software will really try to use all the registers, but there's one caveat. Remember, we may be generating, I would say for real data, we could be generating millions of thread blocks. Okay. So not all the millions of thread blocks will be simultaneously assigned to the streaming multiprocessors. The streaming multiprocessor still has limited capacity and so on. So if you have 1 million thread blocks, chances are you will have maybe a few hundred thread blocks really active in the hardware. Okay, in the streaming multiprocessor, in these scheduling kind of things, right? So only those hundreds of thread blocks will be consuming the real registers. They are not going to consume registers until they are assigned into the streaming multiprocessor. Okay. Now, if you want to use shared memory, which you will not use until MP3, you can declare a variable in the kernel and then use what we call the __ device __ and then _ share _ as the two keywords in front of variable declaration. You can actually omit device. It will still work. So you can just say shared. Okay, but if strictly speaking, it's device and shared. If you want to declare a global variable, you can statically declare a global variable by keyword __ device __ For most of your MPs this semester, you're not going to do this. You're going to be using CUDA malloc to allocate memory. But if you want to, you could. Okay, and then you can declare a constant memory variable outside the kernel by using device and constant keyword. Okay, so these are the places that the keywords that you can use to direct the declaration of your variables into different parts of the memory. And the scope of these variables is very important to remember. The scope of a register is within the thread. It's a per thread, right? I already emphasized it a couple times. And the scope of the shared memory variable will be per block. Each block will have its own shared memory variable. So if you generated 1,000 thread blocks and you declare a shared memory array, that shared memory array will have 1,000 instances. Each one will have different contents. Okay, so this is the reason why I keep going back to the Mickey Mouse, orchestra, because every move that you make, you will be most likely instantiating hundreds of hardware processors. You'll be most likely using up thousands of registers, and sometimes people don't even realize what they're doing. Okay, and in the lifetime of these things are, how long these values are preserved. So the registers are only preserved through the thread lifetime. So when the thread completes execution, it's gone. Okay, and then the shared memory variables have lifetime of blocks. That is, as long as the block, any thread in the block is still executing, that the contents will still be preserved. And the global variables have the lifetime of application. So the entire execution, you can launch multiple kernels. The variables will be preserved across kernels. Okay, and then the constant memory will also be preserved across kernels in the applications. So this brings us to the next MP, and then we're going to be illustrating some of these basic memory usage patterns with matrix multiplication. Matrix multiplication is defined fairly simply as we're going to multiply matrix M with matrix N and produce matrix P. And every element of P is generated by a row of M and a column of N through inner product. Okay, so it's a very, very simple definition. Here we're showing a square matrix multiplication, but in the MPs you should be doing a rectangular matrix multiplication. That means that you're going to have a height and width that are different, and here we only use width for simplicity. So in sequential code, the typical way that we do matrix multiplication is through a three-level loop. Okay, a three-level loop. The innermost loop implements the dot product. So you will take, the innermost loop will take one row of M and one column of N, and we're going to just loop through each pair of these elements and do the inner product, which means multiplication, accumulate into the final value. So that's why we have sum equal to A times B. This is the reason why multiply and add is a very important primitive for both CPUs and GPUs. You have what they call the, multiply and add, the unit in all these kind of, hardware. And so that's the innermost loop. And then we go to the outer two levels of loops. Essentially, in a sequential code, what we do is that we iterate through all the rows of M. Okay, we iterate through all the rows of P, and then so that's the outer loop, and then the middle loop will iterate through all the elements in a row of P, so that we essentially do this. We go through the zeroth row, and then we generate the P element in that row. Okay, that's the second level loop. We go to the next row, so we do the next outer loop iteration. We go to the next row, and then we generate the output element for that row, right? So that's why we have two levels of outer loop. In each of those combinations, we generate one of the P elements. For the P element, we go through the innermost loop to generate the inner product. So this is what we call the n-cubed algorithm, okay? Because if you have n as your width of your matrix, essentially your execution time is proportional to the n cube. And this is a very, very high complexity computational algorithm. And so that there are all kinds of optimization that we do in hardware to speed up this kind of stuff. So when we map that to the GPU, there's a very, very obvious way to parallelize this piece of code. The generation of all the P elements don't depend on each other, right? Every P element can be generated as an inner product of one row of M and one column of N. And they don't depend on each other's outcome. So you can just have a kernel that's mapped to every output P element. So we can have every thread in the grid to generate one P element, right? So that's a very, very simple, formulation. And so if we use that simple formulation, we can have a fairly simple mapping. So here is a very small example where we have a 4x4 P matrix, small P matrix, 4x4, 16 elements. And we can generate a 2D kernel, right? We can use a 2D, kernel to be, to map the threads to the P elements. And obviously, we're going to use what? Block index and thread index dot X and thread dot Y, right? So if you think about this, this is not fundamentally different from the image, the color to grayscale conversion, because in that kernel, we also assigning one thread to each of the output pixels. And you can think about the output pixel as a two-dimensional array element anyway. So as far as the output is concerned, the matrix multiplication kernel that we're going to write will have exactly the same pattern as the image conversion kernel. Each thread will be calculating a column index and the row index according to its block and thread indices. You should be expecting that by now. So for every two-dimensional thread block to compute a block square submatrix, so we're going to essentially assign a thread block to a subtile of the output, right? And that's also exactly what we did with the image conversion. We have every thread block to be responsible for a tile, right? A tile of the output image pixels. So here we show that we use a very, very small block, 2x2 block, right? For this little example. So we see that here, block 0 will cover P00, P01, and so on. And block 01 will cover these. So it's a very natural mapping, right, to cover the generation of the entire P matrix. So here we have width equal to 4, tile width equal to 2, and every block has 2x2 equals 4 elements. If you have a small piece of data like this, and you launch a small kernel with all these numbers, it will actually work. So this is the beauty of some of the CUDA devices. If you need to debug your code, remember some of you said, oh, can I use debugger and so on. The debuggers for parallel processing units are always hard to use, by the way. So they don't try to stay away from them. But you can easily write very, very small matrices and just use the printf and use just execute it on these very small device with very small block sizes. They will still functionally work. That will help you to debug your functionality, and then you scale to big data. Okay. So we can have a slightly bigger example here. So we can have this. We can process 8x8 output matrix. And we can still use the small 2x2 block sizes. It just means that we're going to have more and more blocks. So this is one way to scale to a bigger input data. So width is 8 and tile width is 2 still, and we have each block will still have 4 threads, and then we have 4x4 16 blocks, right? This is one way to scale from small data to bigger data. You essentially generate more of the thread blocks, right? The next one is, well, you can actually use bigger block size. You can have 4x4 block sizes, and then now you only need to have 4 blocks. So this goes back to that 8x8, 16x16, 32x32 example, right? So it should all come together at this point. Now, so this is how we're going to launch that kernel, okay? So we're going to, this is the host code in the host. So we're going to have a width by width matrix multiplication. And so we're going to launch a kernel by dividing the width by the tile width. So that gives us the number of thread blocks in each dimension, right? So that's why we have the first two. So we have, width multiplied by 1.0 and take the divide and take the ceiling function. And this is just to give us the the casting. And then, each block size will be the tile width by tile width. And we launch the kernel, so, we generate all the threads. When we go into the kernel for matrix multiplication, we expect to see a lot of the code that we had in the image conversion, because every thread is still assigned to one of the output matrix elements, two-dimensional matrix element. So we see that, so we go in there. On the other hand, every thread is supposed to be generating a dot inner product. So we're going to be, using a p-value, which is the inner product, output. Okay, the inner product that will be generating out of a matrix, n row and matrix n column. So here is what you should be conceptually thinking about when you, look at the piece of code. So we're going to be generating a column index and a row index for every thread. So that's going to be the column index and row index of the output p element that you're responsible for, that thread is responsible for. And we're just like the image conversion, we're going to have blockdim.x times blockindex.x plus the thread index.x to generate that column number, right? And then we're doing the y version for the row index, right? So this is exactly the same as what we had in the image conversion. So we're showing a very small example here that for block 0, 0, because the block index is going to be 0 here, so essentially the column index and row index are just going to be the thread idx.x and thread idx.y, right? So we're going to have column 0, column 1, and then row 0 and row 1 for these expressions for all those 4 threads. So that's why each of them is going to be covering one of these 4 p elements. There's nothing new here. I'm just giving you the concrete enumeration of what should happen for every thread, okay? So this is how conceptually you visualize the activities of every thread and every thread block. So for thread block 1, because that thread block idx.x value is 1, right? Now everything is added by 2 for the column, but row is still 0 because block 0, 1, the y part is still 0. So the thread block is going to be processing the upper right corner of the P matrix, right? So that's the assignment of thread blocks and threads to the P elements. So now let's look at the kernel code. The kernel code generates the row index and the column index for every thread, okay, for every thread. And that you should go back to the image conversion code. It's exactly the same as the row and the index for the reason I mentioned like 4 times. Now, you still need to test whether the row is less than width and the column is less than width, because your width may or may not be the multiples, right, of the thread block size. So this is the boundary check that you still need to do, just like the image conversion. The only difference from the image conversion code is exactly what each thread does. So in this case, every thread is doing an inner product. So it's going to use the row index to identify the row in the M matrix. It's going to be using the column index to identify the column in the N matrix, right? So when we do the inner product, all the elements from M is going to have the same row index, but then you will use a k variable to walk through that row. And every element that comes from N will have the same column index, but you're using the k variable, inner loop k variable, to walk through the whole column. So this is why you have M, which is using exactly the same row index for all the threads, and then you multiply by width, because you're in a row, you need to pass. You need to essentially skip over all the other rows from the beginning of M. So the row index tells you how many rows you need to skip over, and that gives you the beginning of the row. And then you use K, you use that iteration variable K to increment your index as you do the inner product. For the column, you have exactly this, the symmetric case, because every element has exactly the same column number. So the K is going to give you the number of rows that you're going to go down. And every row actually make you to skip over the entire width of elements. That's why you need to multiply K by the width and add that to the column. So this, if you want to understand this piece of code, you definitely need to understand the row major indexing, the row major layout of C, right? So all the elements in a row are preserved as neighboring elements, but all the neighboring elements of column are actually strike distance away from each other as you access them. So this gives you the basic matrix multiplication loop, inner product loop. And after that inner product loop, you have the inner product value in the p-value. You assign that p-value to the p matrix in your global memory using row and column. With a row major layout, row times what? Width plus column. So the way that you can visualize these things, if we had truly a two-dimensional notation for accessing M, N, and P, we will be accessing M with row K. And we'll be accessing N with K column. And we'll be accessing P with row column as the two-dimensional indexing. And then you convert that into the linearized index through row major layout, and that gives you the code. So this piece of code, if you look at it, is actually amazingly similar, right, to the sequential matrix multiplication code. We basically took out the the two levels of loop and generate the innermost loop body into the kernel code. And this is a very straightforward, parallelization. And I'm going to actually come back and talk about, the life is actually not always this easy in parallelization. So, that's going to be the second half of the semester. So now you know exactly how to write this basic matrix multiplication code. And, you're going to have, a massive amount of parallelism when you have these, let's say matrices of 1,000 by 1,000, output elements and so on. So, but I want to make sure that you understand that this is the beginning, not the end. So, in a typical GPU, when you write this piece of code, you're going to have lots of parallelism, and then you run that code, and if you do a little bit of digging into, the performance of that piece of code, you're going to be a little bit disappointed. Okay, you're going to be just, if you dig into it, it will be a little bit disappointed. So let me talk about why. Let me take the Fermi level, GPU example. In fact, it gets actually worse, into the later GPUs. But for Pascal and Volta, we kick in a little bit more to address this problem, but far from enough. So a typical device will have a ratio like this. We will typically have about, let's say, 150 gigabyte per second memory bandwidth. Okay, so this is the Fermi, GPU memory bandwidth. And 150 gigabyte per second is a very large number, by the way. The comparable CPUs used to have about 25 gigabit per second memory bandwidth. So, for the GPU and CPU, same generation device, you usually have about 1:6 ratio until last year, by the way. Things are changing. The CPU vendors are trying to catch up for technology reasons. But we're not going to talk about that until much later. So 150 gigabyte per second memory bandwidth, and you say, well, what's a big deal? It's a big deal if you do the following. Write your name 1,000 times. Okay, this weekend, when you watch the 2 movies, do this in parallel. Write your name 1,000 times. And I know exactly how long it takes. Because when I was an elementary school student, I asked too many questions, so teachers don't like me. So, oftentimes, they ask me to stay after school and write my name on the blackboard for 1,000 times. And, I did not realize that they were really doing me a huge favor as an engineer. So I know exactly how long it takes. And in fact, if they ask me to write 1,024 times, they will be even doing me a bigger favor. So 1,000 times is, going to take a long time. It's going to take you, it depends on your handwriting. My handwriting is terrible, so I can do it, a little over a few minutes. So now, if you want to know what a meg means, you repeat that process 1,000 times. Okay, now we're talking about real time. Okay, through my elementary school career, I did not repeat that process 1,000 times. Okay, they punished me enough that I stopped asking questions maybe after 20 times. So, so that's a meg. Okay, and then a gig. Okay, what is a gig? A gig is 1,000 times of a meg. Okay, so 150 gig is a huge, huge number. And the kind of technology that goes into that memory system to give you that 150 gigabyte per second is amazing. Okay? But if you look at it from the computation point of view, 150 gigabyte per second is only 37.5 single precision floating point operands per second, because every single precision floating point operand is 4 bytes. So if being able to fetch 150 gigabyte per second means you can fetch 37.5 giga operands, single precision operands per second, okay? Per second. That's still a big number, okay? Still a big number. But when you actually execute that piece of code, you're going to be limited by that number, because you can only operate as fast as the operands can get to you. So you can only operate up to 37.5 gigaflops per second because you need to get those operands to you, okay? And in the real GPUs, if you execute that piece of code on this kind of memory system, you're going to get about 25 gigaflops per second. Close, okay, close to 37.5 with all these other real factors. But if you look at that GPU in terms of compute performance, in terms of the potential compute or peak, what we call a peak compute performance, these GPUs will have over 1,000 gigaflops of hardware execution capability. That is, if you feed the operands to these hardware units quickly enough, the ALUs, the register files, all these things internal to that chip is capable of producing over 1,000 gigaflops of results, okay? And so we're going to be using less than 3% of that hardware. So this piece of code is going to let you use no more than 3% of a typical GPU, okay? And if you look at the next generations, the memory bandwidth is going up, but the compute capability is going up even faster. So the ratio is actually going to be smaller and smaller. So that's why this is only the beginning. You're only using a very, very small percentage of the hardware with that piece of code. Okay? So this brings us to the end. Start to work on MP2. And next week, we're going to begin to talk about how you can go from that 2 to 3% all the way up to maybe 70, 80%. Okay?